Once the nozzles have been verified, then they're ready to be put into a final packaging material. This is for shipping, and this was done with a pick and place operation. It's very common in the semiconductor industry. What would happen is that you'd have to basically align. We performed a on-site inspection as it was placed in the pocket tape as well. And at this point, it was shipped to our customer in a tape and reel format. The fuel injector valve body assembly, which is where the injector nozzle was destined to go, had to interface with several parts. The assembly consisted of a retainer. I kind of point out to these parts. The retainer is the outside piece part here. Then it consisted of a stamped washer, our nozzle, and a valve body. Then finally, the valve assembly was welded together. There's like 10 different welds, a perimeter weld. And then finally, we would inspect our units, both optically with a reflective method, looking for surface flatness, as well as using infrared microscopy. Now that you kind of understand how the packaging is arranged on a fuel injector, at least on the valve body, I wanted to kind of go over some of the problems that we encountered. There's both problems are things that you fix along the way, and successes are those things that you have fixed and you've continued on. We'll start with the problems, and we definitely did fix these particular problems along the way. Most of the problems dealing with our product dealt with our nozzle in the assembly, and what would happen is that you would end up cracking or breaking these nozzles. They're very easy to detect, but we wanted to get our defect rates down to a low and acceptable minimum number. The biggest contributors to the problem basically was bending stress on our nozzle, and that was induced by basically two different types of features. First one deals with the foreign material in the package assembly. And this starts with foreign material that's created into the pocket of the pocket tape that's sent to the factory, as well as foreign material that's generated during the handling operation and getting it into a valve assembly. The package components also contributed to the bending stress problem. We're going to go into those in a little more detail here. Bending stress, which would basically put a high amount of tension on the inlet surfaces of the nozzle, and cause a crack or damage these particular nozzles. Because what would happen is in the stack of the assembly, if you get a particular particle, whether it's silicon or metal or something else, you would basically induce a moment on that particular surface, would cause high tension in these areas, and then can cause the nozzle to crack. Sources for this foreign material dealt with our wafer saw processing, and what the condition of the nozzle as it left our factory, handling damage that could happen in our pick and place operation, as well as in our saw operation. We had handling damage at our EFHD plant, and we had basically some issues with the industrial environment and what their expectations were in handling this device. At FMI and in the saw process, here's a good example of something that's very, very small and cause a lot of problems. In our dicing saw process, it may be difficult to see, but this is the full height of our nozzle wafer. And it's 16 mils. And down here in this little square box is a edge remnant from the saw operation. this little box is, it blows up into this particular picture here, which then brings you over to this picture on this side, and this has a little bull nose on it. That little bull nose, only 10 microns big, had a propensity to fracture off at the wrong time. And we had to clean up our saw process to eliminate this as any sort of problem. Because what would happen is, under handling conditions, anytime you handled these edges, this would be the first thing that would break off and would fracture off and create foreign material. This foreign material would then be trapped in the fuel injector assembly. This is a picture of what some of those edges could do and some of the EFPHD and FMI handling damage. Along the edges of the die here, there's a chunk out right here. This could have been caused by one of several different operations, including that which I just showed you, the SEM photograph, with the bull nose that has fractured off into a chunk or a sliver. In this particular case, here's a corner that's slightly knocked off here in the retainer assembly, just prior to the valve body insertion. This chunk of silicon now will be placed over here, and under pressure of the assembly and the welding operation could induce a moment in these particular orifices, causing a crack. The last thing I spoke about in the foreign material dealt with the industrial environment, and I wasn't quite sure how to describe this, but I just have one word here: cleanliness. It's amazing the difference in expectations between the micro machine manufacturers and maybe the packaging people later down the road who work in an industrial environment much different than our very clean micro machine environment. I think that was one of our weaknesses on our launch. Basically, there was sets of expectations that people thought they were the same, but they really were not in practice. We always thought that things were as clean as we would build them in our fab in this fuel injection assembly area, which was a very clean area for an industrial area. But it wasn't ever quite clean enough, at least in the beginning of this project. And just a simple thing like where in the semiconductor environment, if you had a silicon chip someplace, you would blow off the silicon chip with some dry nitrogen and be done with it. Now, that doesn't exist in many of these plants. So what would happen is you blow it off with some semi-oil bear. And what would happen is that the particle wouldn't go away, and it would attach itself and create a trail of debris along the way in the handling system. That was something we were able to overcome. So it's just kind of just a source of some painful experience on where some of these things start generating from. So cleanliness is very, very important in the handling of many of these MEMS devices. And in this case, for the silicon nozzle, it was very, very important. Sources of component stress dealt with the condition of the assembled components. The valve body, in particular, had some problems that we weren't quite aware of the issues. The valve body is this part of the assembly again, and it mates directly with the silicon micro machine nozzle. How well it mates, how flat it is, what kind of condition the surface really is really pretty important. The start of our product, or at least in the development phase, what we found is that the surface of the injector, although it was flat in spec, which we wanted it to be under 5 microns of flatness, we found that the valve body was more of a concave salad bowl condition. This is a plot contour plot of the surface of the valve body. And this is the surface that would mate with our nozzles. And it's accentuated so you can see the difference in condition. But this is using their standard equipment. And what would happen is that you'd have a lobes that would come up off the perimeter of the valve body. And this is used to mate with our part. When this was combined with the compressive force of the retainer, it would induce a certain amount of bending moment on the surface of the nozzle or in the overall structure of the nozzle, which would translate to a tensile load and cause a damaged nozzle. Simple process change changed the valve body condition tremendously. This was just a change in a grinding process that has virtually the same flatness, but if you notice that the profile is more consistent and lends itself to a better mating structure and doesn't induce a bending moment in the assembly. So what happens here in this particular assembly, just a warning, was the fact that this grinding operation, although met specified parameters, really didn't meet the intent of what we wanted, causing a bending moment in this area as the nozzle is clamped into the system. Early on, we found that infrared inspection proved to be quite informative at detecting any sorts of cracks. Very conclusive. We were able to verify all our nozzles very easily using this type of technology. And silicon is transparent under infrared frequencies, I think. And it's just dependent on the thickness of the silicon as well. But if you have something that's greater than 900 nanometers in wavelength, what would happen is that you would be able to see right through the silicon. Depending on the typing lighted conditions and things, you'd be able to even see the grinding surfaces of the parts past the silicon. So it was a very good method of detecting any sorts of problems with the assembly. Kind of go over the summary of what our valve assembly went through for our product and mating this MEMS product to a machined industrial environment product. Basically, you need to control the bending stress. This is particularly important because of the geometries of our nozzles. Then verifying through infrared inspection really provided not only containment, but also investigative tools to the root causes of our problems. Just want to go over a product summary here. Really, there was 4 million injectors that we considered successfully made using this technology. And they provided very consistent flow control and were a nice, I guess it's kind of a different MEMS product, but it was a very nice product. Provided excellent deposit resistance as well as flow control. The packaging process was very important, and we had gone through some, I'll say, lumps and bruises to get it in good condition. The SMM product was viewed as expensive. A problem with our technology, at least in this particular application, is that silicon real estate is pretty expensive. And there's always other technology that's competing with the same sort of functionality that ours can provide. For our nozzle, there's other competing technology, EDM, stamping, and others, plating. They're constantly battling for which is the least expensive, the most durable, the highest quality. And in this case, SMM had very high quality, was very durable, but the costs exceeded the targets that were set up by the needs of this injector. We're not talking about an awful lot here, but we are talking about nozzles that are and different types of technologies are continually competing over the same sort of performance and cost targets. The automotive industry is very cost sensitive. It's also performance sensitive. In the engine environment, it's very difficult to have a marginally better product perform better at all in the engine level. And our SMM injector at the time was a much better product than the other products at the time. We reduced the particle size from 200 microns down to 120. But some of the other competing technologies quickly caught up with us and were slightly inexpensive. And so at that point, that was the main reason why this particular technology was phased out. I wanted to go over a future product slide. We have a future product that we're developing and have been developing. It deals with 2 layers of silicon fusion bonded together with an internal cavity or turbulence cavity. This would reduce the particle size even further, and from 120 down to 50, and control spray angles and spray distributions better. This is something that is in the, I'll say, in the wings for our company. It will just depend on what sorts of technologies they choose to combine with the engine platforms to solve their engine performance needs. This is one of those tools in the toolbox that the engine people will end up evaluating for this type of for future use at Ford. I think that's really pretty much it.
Okay, thank you, Hugh. We have maybe 1 or 2 questions here locally. We ready? Yes.
Hi, I'm Kathy Powell again from the SMTC, the Southeast Manufacturing Technology Center. What about material compatibility? You've mentioned the cleanliness and the surface finish. What kind of issues are there about material compatibility?
For corrosion mechanisms?
For corrosion or any other wear?
This type of product has been extensively tested prior to implementation into production. There's been just many fleet builds, number of engineering tests. I have a foil here that would indicate, I'd like to show you maybe. I'll kind of lead you over to this. Here's a view of the valve body assembly again, and what we're going to do is we're going to look at a single orifice of a fuel injector. Now, this fuel injector had gone through a fleet evaluation. Basically, it had 180,000 miles on it, and they used about the cheapest gas you can possibly use on it. And after 180,000 miles, after 180,000 miles, it still wasn't within specification. It was non-clogging. Matter of fact, if you were to take a look at this fuel injector, you'd find this burnt, ugly fuel injector. The only thing that was left that was still shiny was the very tip of the injector, and it looked very much new. It was very deposit resistant, and so from that particular point of view, there's been actually quite a bit of testing. Ford's very careful about implementing any sort of fix or product or whatever into production until after it's been thoroughly tested and evaluated over generally a period of 3 years. Okay.
We have 1 telephone question. We're ready. Go ahead.
Hello. This is Terry Sharton from JPL. Given the problem that you mentioned of the stresses and the roots of these square corners in your orifices, I wonder why these holes aren't round. Is there something inherent in the machining of this silicon that demands that they go along the crystal boundaries, or why are they sharp square corners?
Well, it goes back to the basic processing of the material. We're processing a 100 material and etching it along the 111 crystal planes, because the crystal planes offer very slow controlled etch under wet etch conditions. That way we can hold our tolerances to be very tight and repeatable. That was the essence of utilizing this type of material and this type of processing, was to create this type of hole. In order to do that, we needed to use the tools of our industry. Basically, in this case, it's utilizing the 111 plane as the slowest selective etch plane in our etch bath. And with this, you're able to target very easily the size of the orifices and maintain that geometry. A circular hole would require a different type of processing, and probably would have been less susceptible to stresses and any sorts of breakages. However, although these things are very, I won't say susceptible, but provided the packaging is adequate, there hasn't been any sort of ongoing problem at all with this type of technology. But I would agree that if there could have been a way at controlling the geometry at that level, then there'd probably be much less stresses associated with that assembly.
Thank you very much. I have another question here, if I might, from another gentleman.
Hello, this is Gerhard Klose from JPL. I was wondering what kind of specifications you have and how you control the taper angle that you show in the cross section and the edge sharpness. Thank you.
Okay. I'm going to go back to an earlier foil. Like, if I may. Maybe I won't. Let's go back to this earlier foil. The inherent properties of the silicon and how we're etching them control this taper. These are inherent in the crystal lithography of the material, and they're along the 111 planes. This essentially makes a 54.7 degree angle with the normal surface. And it's inherent in the basic material. That was one of the reasons they thought it would make such a good nozzle. And it really does from that standpoint. Did that answer your question? Is there any other questions, CJ?
Doesn't look like there's I have done one question myself. Have you thought about coating your nozzle with some material which either is compressive or tensile, so that your braking by the stress concentration is reduced?
Yeah, this is you're talking about like a gasketing material.
No, over the whole surface of the nozzle.
Oh, you could probably put some sort of nitride or some other sort of maybe conforming material, and maybe it would fill in some of these corners and things. Yeah, we've done that. I think one of the biggest problems with that was that in order to fix this, it was kind of laid into the program. And even though this may seem like an easy fix, because we've done many different experiments in improving the feature robustness, you can do some etching, which would improve and smooth out some of the sharpnesses of the features, which would reduce the stresses and improve like the braking strength of the material. But you got to be very careful about how you implement something like this, because as you come up with a fix, if you don't have 3 years of track history behind you, it's very difficult to go forward. There's risks of what will happen after that. And so a solution similar to what you're suggesting could be implemented, but it would be implemented very carefully, of course.
Our next speaker is Dr. Howard German. Dr. German is a director of technology for EG&G IC test sensors in Milpitas, California. And he's responsible for a group involved in the design, fabrication, and testing of advanced MEMS device prototypes for commercial customers in a variety of industries, including automotive, medical, aerospace, and industrial. He was the founder of microsensor technology, which commercialized the gas chromatograph and later joined transsensory devices, which merged with IC sensors in 1986. And his topic today is development of microfluidic systems.
Thank you very much, CJ. And good morning or good afternoon, depending upon where you are. My talk today is about the development of microfluidic systems. I'm going to first talk about some components and then talk about the systems that are enabled by those components. The outline of the talk is as follows. I'll first review some micromachine fluidic devices such as channels and restrictors, then talk somewhat more on the development of a bimetallic valve that we've been working on at IC Sensors for some years, and the commercialization of that valve. And then an example of a few fluidic systems that use both that valve component and some other fluidic components, and then some conclusions and perhaps a little bit of advice. As is perhaps clear now, and example of an orifice, of course, was previously shown, it's possible to make a wide variety of grooves and orifices, channels, and whatnot in silicon by a series of masking, lithography, and etching steps. These can be done either using plasma etching techniques or, as Hugh was discussing earlier, anisotropic etching techniques, where the walls of the channel are defined by the crystallographic planes in the silicon. One generally etches a groove in the silicon, and then in order to make that into a channel, caps that piece of silicon by either using another silicon wafer or often by anotically bonding a Pyrex glass wafer to the top of that wafer. I'll present an example of a flow restrictor using that technology.
Hello. I just add additional comment about previous the silicon-based micro nozzle. I already give you additional notes through the chat, so that recently I think all of you learn about 3D printing become one of the new technologies, so that like GE actually try to come with 3D printing to make this kind of nozzle for the aircraft engine, so that do you think so? The one you have seen using silicon, micro machining, right? In this talk, actually, it's done in 1996 something. So that time they use wet etching, but now I think, of course, we also have new deep IE dry etching. So we can really control much better in terms of fabrication of the silicon nozzle, other kind of device, microfluidic device. Okay.
On the next overhead. You can also make filters. By this I mean traditional particle filters by having a large number of these channels in parallel. These filters are limited in some respects compared to conventional technology, but also have some other benefits. All of the dimensions on these filters are defined in one way or another, either by lithographic tolerances on the process or by the thickness or the depth of the channel or groove that you want to make. This is in some contrast to conventional bulk filters using, for example, sintered metal technology, where you have a rough idea about what the pore size of the filter is, but no exact knowledge of the actual geometry of the filter.
So I also add some comment about this filter, right? The Jose is this kind of automation machine for Ken Dynamics actually is, so we actually try to do automation, right, for this kind of microfiltration, right? So this filter has many different applications, right? Not only do filtration about maybe some cancer cell, filtration about bacteria, or even some micro nano filter can also maybe filter some of the dust particle, right? So that the filter is actually one of the important microfluidic component, okay?
There are a whole variety of mixers, splitters, and reaction chambers that are basically a combination of these groove and channel elements combined with various other devices to implement all of these particular parts. I'll talk a little bit about a reaction chamber for a biomedical use a little bit later. About the next level of complexity on these kinds of parts are a whole variety of valve structures that have been described in the literature. I'll talk about one particular normally closed device that we've been working on, but there are a variety of other normally open, normally closed, and one-way or check valves that have been described in the literature. And I have a small number of references in the back of my notes to some review articles about other fluidic devices. So if you're interested in some of these elements that I don't have time to discuss today, you're welcome to take a look at those references, most of which are quite complete. There are also, as you've heard, other sorts of devices that have been made, flow sensors that haven't been described as of yet. Historically, the flow sensors that have been made for fluidic systems have used either differential pressure measurements or various thermal techniques to measure flow. And pressure sensors are now perhaps the conventional way of measuring pressure nowadays is with a silicon micromachine device, quite a bit different than perhaps 10 or 20 years ago when other strain gauge or other bulk or macro machined devices were primarily used for pressure sensors. This has driven the cost of a typical pressure sensor down by at least an order of magnitude, and tens of millions of these pressure sensors of various sorts are made every year. And then it's also possible to make quite a wide variety of what I call here property detectors, which includes things like thermal conductivity, density, resistivity of the fluids by combining typically a channel, an etch channel, with some sort of either electrical or optical component. One example of a moderately complex, or depending upon your point of view, relatively simple flow restrictor is shown in cross-section here. This is a part made from two separate, in this case, silicon wafers. In this bottom wafer, a series of three silicon etches are used to define through holes through the wafer from the backside, manifold areas around the part. And here in cross-section are shown both some small grooves that are used as filter elements and a somewhat larger V groove, which is the main restriction in this particular part. This particular part is designed for medical applications where, for example, a drug, chemotherapy agent would be introduced through this at a particular inlet pressure of, for example, 10 psi, be then pushed through this restrictor at a very controlled rate and be sent off to the patient down from the downstream side of this particular part. In this particular part, their desired flow was on the order of a half an ml per hour, which is really not very high and results in this V groove being quite small. the top width of this B groove is about 22 microns wide, and because of the crystallographic nature of the material, about 15 or 16 microns deep, which is somewhat smaller than the proverbial human hair. One of the things that you may recognize from conventional theory is that the flow through such a laminar flow element goes as the fourth power of the effective diameter of this part. So we need, in the processing of this part, in order to maintain 5% repeatability in the restrictor itself, the width of this groove has to be kept to within about 1% of 22 microns, which is only about 2,000 angstroms. Now that's actually below the resolution of a typical lithography step, but it is possible to maintain the width of such a groove to that accuracy without going to enormous expense or complexity. This part has undergone a set of patient trials, and we expect this part to be in production relatively soon. I should point out that there is conventional technology that can perform this function to some degree. That technology uses capillary tubing, the same sort of tubing that's used in thermometers, and that provides the restriction itself, but not the filtering action that's provided in the silicon part. We can integrate these filters quite inexpensively, and essentially at the same time we're making the grooves. So we can add the filters, and that's of fairly significant benefit in this particular application, where it's very difficult to ensure that the particular drug or intravenous fluid is completely particulate-free. Next part I'd like to talk about, which is also in commercial production, is a bimetallic microvalve that we've been working on for some time. This particular part also consists of two silicon wafers, which are bonded together at the wafer level. The rough process sequence in order to make this part is a set of hinges are put in. This picture is actually roughly circularly symmetric. I'll show an SEM here in just a minute. A hinge is made which goes around the entire periphery of this part. This hinge will provide two functions. It will both thermally isolate the active diaphragm area and also provides an approximation for a simply supported boundary condition for this part, which is necessary for the particular mechanical action. A series of resistors are implanted in the diaphragm in a similar way to the piezo resistors mentioned earlier. In this case, these resistors are only going to be used for heating this element, not for strain sensing in the silicon. Then a set of contacts are opened up. A relatively thick layer, in this case about 7 microns of aluminum, is deposited and patterned. And finally, the wafer is a bulk micromachined, etched in a potassium hydroxide solution in a similar fashion to the Ford orifice described earlier, until a diaphragm is left that's also about 7 microns thick. Then that particular actuator wafer is bonded to a valve seat wafer that has a relative.
Okay, so I just add additional comment for this particular part. So this kind of microfluid, the device, mixer or controller has some unique application. I just show you one of FDA approved this kind of microfluid pump with sensor for diabetics. You see, so those are people with diabetic, they have to monitor about glucose in the blood and then do this provide insulin, right? So that this become one of I think quite important application for microfluid with sensor. Doing that, so that I just let you know that this microfluid is one unique I think the opportunity for our this kind of micro machine. So that okay. Do you have any question? If not, well, let me just try. I just give you one of this real product, right? This kind of approved by FDA. Okay.
Shallow etch around the seat area. After the part is diced and packaged, a package is made that has a hole down through this center part, which is actually the exit of the valve. There's an entrance to the valve and a set of holes around the diaphragm that allows the gas to enter in this part. When power is applied to this diaphragm, the bimetallic action between the silicon and the aluminum causes this bossed area to move up, opening the valve and allowing gas to pass through. This I'll show some graphs of what the flow versus power of this part is a little bit later. This part is normally closed, and it's perhaps not too clear from this cross section. There is a significant amount of residual tensile stress in the aluminum as deposited. That causes this boss to be forced down against the gap, So this valve doesn't open until enough power is dissipated in the diaphragm to provide enough restoring force here to open up this particular valve. This valve has a number of interesting characteristics. It's a bulk micromachine device in comparison to some of the earlier described surface micromachined components. In this case, we essentially require a bulk micromachine device because the forces that we desire out of this part are larger by something like 4 or perhaps 5 orders of magnitude compared to the kinds of restoring forces that are available in a electrostatically driven surface micromachined element. It has normally closed response characteristics, which are important for many applications where you'd like the valve to be closed when no power is applied. It's bonded at the wafer level and only 4 millimeters on the side. That results in a relatively low die cost for this kind of part. We get about 350 parts on a 4-inch diameter silicon wafer, which represents a die cost on the order of a few dollars per part. It has a relatively simple and easily controlled bimetallic actuator. It's controlled simply by the amount of power that's dissipated in the part, and that's relatively easy to meter. It has a flow that's relatively low on the scale of what most people may be used to for solenoid parts, on the order of 100 or 200 SCCM at something on the order of say 10 to 20 psi of differential pressure. It's fast for a thermally driven part, but relatively slow for an mechanical part. It has a switching time of about 60 milliseconds. But its proportional response does allow a very simple either pressure or flow regulator circuitry, which is a big advantage. It can be controlled over a range of greater than 100 to 1 in flow, and the leakage, which is actually built into the part to avoid sticking under most circumstances, is a small fraction of an SCCM, which is about 5,000 times less than the full-scale flow. This is adequate for a number of people in a variety of applications, but it is not a perfectly closed part. Flow performance is here. I apologize, the scale has been dropped here. This is in milliwatts. As the power is increased going into the part, there's no flow until that residual tension in the aluminum is overcome. The flow then rises fairly steeply for a variety of pressures. Since we're applying the inlet pressure to this valve on what we would call the outside surface of this part, as you increase that pressure, that also provides a closing force on this part, requiring somewhat higher power to open the part with higher input pressure. And I do have an SEM, I think, right here. Of what this part tends to look like. We'll see how this comes out. This is the nominally, well, it is very close to circular outside hinge. The gray area right here is the thick aluminum over the thin silicon diaphragm. In the center here is a boss, which is actually octagonal, but on the top surface we can make an inner hinge, which also provides a thermal isolation function with a circular mask feature, and 2 electrical connections, one going to a contact around the outside of the part, and the other going onto the inside to a contact on the inside of this part. As current is passed through this device, it goes radially through an implanted area around the entire part, making a part that's very close to being circularly symmetric. And also, just to give you a little history of this part has been worked on for quite some time. We developed with Steve Terry and myself a variety of different valves in the 1970s for use in a miniature chromatography system that I'll describe a little bit later. These, however, used either pneumatic or solenoid drivers for the parts, but were quite successful in that application, quite expensive also. A normally open valve was developed for one of our commercial customers, PerkinElmer, in 1988, and we reported that at the Hilton Head Conference in 1990. But it didn't have some of these thermal isolation features and required quite high power on the order of 1.5 watts. The normally closed valve was subsequently developed, and a paper was presented on that part at Transducers 91. I believe that was in San Francisco. It had these oxide isolation features, and its power was down by about a factor of 5 or so from the earlier normally open part. A few customer parts were shipped in 1991, but this was with relatively crude packaging. So I think you can appreciate by now the packaging of these parts is very critical. Typically, it can be as difficult to develop packaging for the part as the chip itself. Subsequently, when funds and people were available, the package was redesigned in 1993. Additional samples were shipped at that time, and some customers were, as I say, acquired, I guess, at that point. And low volume manufacturing of this part continues to this day. There are some difficulties with and there have been some difficulties with the commercialization of this part. One is that it does not directly replace anything that's on the market today, although it has similar function to some extent with solenoid valves. There's no drop-in replacement business, even though at high volumes we expect this part to be cheaper than a solenoid valve. You can buy some very nice, relatively high-performance solenoid valves at quite low cost these days. The flow range of the micromachine valve is substantially lower than most conventional valves. Now, this is both a disadvantage if you're trying to sell into a conventional marketplace. It's certainly an advantage for many new applications that may require control of flow at very low ranges, where the micromachine component actually has significant advantages. But if you're trying to sell into a conventional application, its flow range of being different than the conventional part can make that somewhat difficult. It has potential problems with contamination, which are perhaps more severe than with conventional parts. We actually have a sample here. The part is currently packaged in this form, just to give you some idea about the size. We have the part mounted on a small ceramic base with a plastic cap. Actually provide a stainless steel frit filter on the inside of that package. And I don't know if I can do this any better. And that frit has nominal 5 micron pore size. So we filter out 5 micron size particles and above in the package itself. But clearly the size scale of this part does require that the gases that are passed through it be relatively pure, or else you'll eventually clog the filter that's built into this particular package. We've had only a moderate amount of engineering time available to develop this part. Most of our people are engaged in other projects which have somewhat higher priority to the company at this time. So we haven't had the time that we've really wanted to support custom packages, changes to the die itself. And the production volumes depend upon sales of systems to design to use only this part. And that's relatively important. You have to provide both the initial die development, some kind of packaging to get that packaging out to your customers. They have to use that packaging to develop systems, but your production volumes don't occur until those systems finally end up going into production. And this entire process can take quite a few years. One of the things I didn't talk about is there are some problems in this part using pure aluminum as the actuator metal. In some sense, pure aluminum is quite good for these kinds of things, but pure aluminum doesn't have the compressive yield strength at temperature that a number of other metals have. And we've recently received funding from the Defense Advanced Research Project Agency to take a look at some advanced actuator metallizations for these parts. And we believe that these will find their way into improved valve parts in the relatively near future. Now I'll talk about a few examples of fluidic systems that use these and some other components. First of all, a gas pressure regulator. Then I think briefly a description of the integrated gas chromatograph that we worked on some time ago. A more recent project involved in DNA analysis using the polymerase chain reaction process. Capillary electrophoresis, which is a technique for separating biological modules. And I've also briefly discussed this particular fluidic system used for infusion therapy. A simple pressure regulator using these components can be very easily made. Consists of a normally closed valve chip, a silicon pressure sensor. In this case, we use a bulk micro machine pressure sensor that we make ourselves. Some very simple electronics, an amplifier for the pressure sensor and a comparator. One provides a DC or a slowly varying AC signal into this part. The pressure from the sensor is compared to the desired pressure with a comparator, which directly drives the valve chip. If the pressure is lower than what's desired, the valve opens up, increasing this pressure. We also include a silicon restrictor chip, since if you want to decrease the pressure in one of these parts, and there may or may not be any flow going out to the system, you need to vent a small amount of that gas out in order to reduce the pressure. And we use a silicon flow restrictor for that purpose. With no power applied to this entire system, there's no output flow due to the normally closed valve here. This pressure sensor can be either gauge or absolute. We happen to use a gauge device for this particular part. And this restrictor, as I said, is optional in a number of applications where one might know that flow is always required. Obviously, there would be no need then for this restrictive vent chip. To give you some idea about what's possible with a part like this, using very inexpensive electronics, This is a graph of output pressure in PSI, and I also apologize that the scale here got somehow lost in printing. This is in a scale of minutes. However, it actually really doesn't make too much difference here what time scale one might look at. These two lines that I drew are at, I think, plus and minus 1,000th of a PSI, around 5 PSI or so. The actual standard deviation of the pressure measurements here is on the order of a 10,000th of a PSI, and this is irrespective of the flow through the part. It's actually probably as good as the pressure sensor chip that we're using in this part. And in fact, in this particular case, the measurement of the pressure is from the same pressure sensor chip that's controlling the pressure, which is not perhaps fair in one sense, but I think is a reasonable indication of how stable a device like this can be with, again, I repeat, extremely simple electronics. The resolution and accuracy is, in this case, probably limited completely by the accuracy of the pressure sensor. The parts that we make typically have stabilities that are much better than this 1,000th of a percent full scale. And its flow performance is also pretty reasonable, very constant pressure until you get out to the maximum flow that the valve can supply, and then the pressure drops off. I'd like to just talk for a few minutes now about the uses of these fluidic components for an area that I lump under analytical instrumentation. There's continued interest in this field. The inherent fabrication precision.
Well, I made the comment for this particular talk, right? I already give you a chat now through a chat so that at least now there's a product, right? For this kind of microfluid device and a component. Now, one of the important application is for analytical chemistry equipment, right? Micro GC, micro gas chromatography. I show you that Agilent had a real product, micro GC, right? With micro machine the sensor. Right, this is TCD, right? Micro machine thermal conductivity detector, right? For air pollution analysis. So that is something real application. Okay.
That we've talked about allows us to make devices that are extremely difficult to make with traditional techniques, and smaller devices in this sense are inherently faster than larger ones. There is the potential for low cost of making these devices, and that can be low cost either for a disposable unit or for an instrument that's reused. And it is relatively easy to integrate a variety of flow elements, electrical, thermal, and optical, either on the same chip or through hybrid techniques in using separate chips for some of these elements. And these small instruments typically use very small sample sizes, small amounts of reagents, which in some cases can be very expensive, and typically low power, which can be important in some portable applications. An example of such a system, which goes back to our work at Stanford now 20 years ago, is a gas chromatography system. Briefly, a carrier gas, in our case helium, is passed down a very long channel. Part of that is coated with, for example, a hydrocarbon or silicone oil. A sample is injected into the head of this column by an impulsive sample, which starts out at the head of the separating column as a mixture of components. Through a process of diffusion in and out of the column lining as it proceeds down the column, is physically separated into its constituent components, ethanol from methanol, for example. And then by passing through a variety of detectors, in our case, a thermal conductivity detector, individual peaks are measured, which are directly proportional to the concentration of that particular constituent in the sample gas. This serves as a sort of a prototype for all of these sorts of systems. Typically, there's some kind of problem with getting the sample into the particular part, some kind of either separating or reaction going on with the particular reagents or samples, and then typically some kind of detector involved in measuring what you have. Somewhat different device, but one that has some of the same sorts of problems, is a recent project that we're undertaking with PerkinElmer Applied Biosystems Division, and that's to use silicon micromachining techniques to make the so-called polymerase chain reaction devices. This is a technique where DNA is sequentially split and then annealed, where the two separate strands of DNA are reformed with a series of enzymes and reagents in these chambers by cycling between two very precisely controlled temperatures. This is a technique that's widely used in conventional instrumentation these days. but has not been thoroughly analyzed on the small size scale that we're talking about. It looks like we've lost the 2 microliter volume silicon-based chambers that we're making. Those chambers are roughly 20 to perhaps 40 times smaller in volume than what's typically used in a conventional device. There's a possibility of real-time monitoring of these reaction products through fluorescence chemistry that's been developed for conventional instrumentation. And we also can integrate various separation schemes with these reaction chambers. One of those separation schemes, which is also has a great deal of interest these days, is to use a so-called electrophoresis process, which is similar in some sense to the gas chromatography.
Well, I also add additional comment for this one. Again, this video is 1996, right? So that all this kind of presentation now have a real product, right? The PCR now actually there are several companies make this kind of microfluid PCR product. For example, BioRed company, right? And also some droplet-based microfluid device for DNA sequencing. So there's a series of companies try to make this kind of microfluid PCR product, right? The same thing for this CE, capillary electrophoresis. You can also find those companies try to make a real product like Caliber Life Science in the United States really make this kind of microchip-based electrophoresis system.
System, except in that a sample is injected at the head of a column, separated and detected. In this case, however, the transport of the material is all done via electric potentials that are applied across various ports on this particular device. These molecules are somewhat ionic in the presence of a high electric field. There's differential migration of these components down a column, but by the time they reach the detector, they've been physically separated and can be detected by a variety of techniques such as fluorescence. So in conclusion, I hope I've shown that micromachining does allow the fabrication of quite a wide variety of very small, potentially inexpensive fluidic components. And these components can be integrated either monolithic or complicated systems. But I feel that I must point out that the application for these parts must justify the development expense, which in some cases can be considerable both in money and in time. And as has also been pointed out, both the design and the testing of these small-scale analytical systems can be quite difficult. The development times still are typically very long, which has a lot to do with our ability to model and analyze these devices before they've actually been made. And as a final point, I'd like to emphasize that you should really make sure that you know how you're going to manufacture and sell the final system before you get too deep into the development process. Thank you very much.
Thank you, Hal, for the informative presentation. We are now open for questions. Looks like we don't have any incoming phone calls, so let's start with questions in-house.
Al, from your presentation, it looks like this is designed mostly for low pressure applications like 20 psi and lower, or is there applicability to higher pressures or not?
Well, for a variety of the restrictors and flow sensors and all, the pressure is not typically limited by the silicon component, but often limited by the package that it's put in. The very high pressure applications typically require very rugged stainless steel packages just to interface with whatever that high pressure medium is. The particular valve that we described is a relatively low pressure valve. That's a trade-off versus flow versus pressure in a lot of cases, but there are some other actuation technologies that can achieve on-off flow performance of at least hundreds of PSIs, if not a few thousand. So it is possible to use relatively high force. Actually find that a large percentage of the applications are typically below 100 PSI.
Thank you. We have a couple of more questions, I think, from her.
Hi again. How are these systems modeled and designed? And most of them seem to be for high volume applications and low pressure and stuff. But can you go on through production, just kind of a scope?
Yes, the design of these parts is actually quite challenging. And in many cases, the design tools to make these, as I think was pointed out in some of the earlier talks, are relatively crude. In most cases, on the size scale that we're talking about, conventional conventional analytical theories are still applicable. So those sort of techniques are quite valuable. I have a couple of slides that were made for us by a group at the CFRDC, Computational Fluid Research, Computational Fluid Dynamics Research Company. I think that's what it stands for. In
CFDRC,
Alabama,
this company.
A mode finite element simulator that's can handle both thermal, fluid, and mechanical finite element analysis simultaneously. And they were kind enough to try out their tool on our particular valve structure. Well, to see, this is a three-dimensional cutaway view of a valve. The yellow arrows here show the gas flow through the part, through an inlet port, through the valve, up, under, across the valve feet, and out. This particular program can model all of the forces applied by both the thermal actuation of the part and the pressure forces developed by this part. But this is a tool that's just coming on the market, and this part, frankly, was designed without the help of these particular techniques. It's my view that tools like this will be increasingly valuable in the design of these parts where there are mixed technologies that one simply can't use simple mechanical finite element design always in modeling these parts.
Thank you. We have one more question now from satellite site.
Hello, yes, I'm from Garcia from Vanderbilt University. My question was on using the bimetallic actuation mechanism for the from active materials like piezoelectrics for a fast responding valve, or perhaps even some sort of shape memory alloy for a slow responding valve like the bimetallic.
As we've considered those, it turns out that there are advantages and disadvantages for all of those actuation techniques. There are groups at other places that are both making shape memory actuated valves. There are specific references to those in the papers that I've referenced in the back of my talk. The piezoelectrics that are available in deposited form is typically zinc oxide, which makes a reasonable piezoelectric sensor, but a relatively poor piezoelectric actuator. People have used conventional PCT ceramics in various bulk forms, simply glued onto silicon parts to act as actuator elements. And they are certainly capable of providing very high forces at the cost of having this additional assembly technique. So there are a variety of other actuation schemes that can be used for various historical reasons, and because we think that it's probably the easiest way to integrate the actuator with these parts, we've chosen to concentrate development on these bimetallic actuators.
Okay, thank you.
Thank you. Welcome back. We begin this segment with our last speaker, Mr. Christopher Beatty. Mr. Beatty is the product engineering manager for new products at Inkjet Supply's business unit for the Hewlett-Packard Company. He has been with HP since 1982 in various areas of microfabrication, including integrated circuits and micromachining. He received his BS in mechanical engineering and chemistry from Michigan State University and a master in material science from University. He'll be speaking on development of inkjet, HP inkjet printer. Chris.
Thank you, CJ, and thanks for inviting me. Glad to have this opportunity to talk about HP inkjet. It's kind of a logical follow-on from Hal's presentation, in that this is a very specific example of a hydraulic fluidic system that has developed over the past dozen years or so into what is probably the biggest micromachining-based business in the world. It's measured in the billions of dollars at this point, and that's strictly for the inkjet pens, not counting the printer systems that they go in. So what I'll be talking about is the evolution and development of the microstructures that go into the inkjet pens. So before we get to that, looking at kind of an overview here, we're going to talk about some inkjet basics. How do these pens fire, and kind of go through the features that are common to all the pens, so it'll make more sense as we look at how they evolved over time. And then we'll go through each of the four generations of pens, the major families of pens that we've developed, and then finally look at kind of where some of these trends are going as we move into the future. So I'll start off in a very generic sense, looking at a two-dimensional view of a firing chamber. And if you can imagine this either in sort of a circular or a rectangular chamber, this down here is a representation of a thin film heater that is driven with an electrical pulse that is approximately 2 microseconds long, some a little more, some a little less. That's tuned for the firing of the chamber. And the inks, which are aqueous based with various pigments, but primarily water. When you fire that pulse, you cause a bubble, which we call a drive bubble, as it drives the droplet out of the chamber, to form across the surface of the resistor. The drive pulse is so fast that essentially you get what is called homogeneous boiling or plate boiling, where it doesn't form in one localized spot like it does on, say, the bottom of a boiling pot of water, but forms uniformly across the surface of the resistor to create kind of a planar wavefront, which starts pushing the ink out of the chamber. Now, there is a little bit, there's an ink entrance into the chamber, and so a little bit of the ink is actually pushed back by shaping is forced out of the hole. So if we look now a little farther into the firing sequence, this is at 15 microseconds. The drop has been pushed most of the way out of the chamber. The tail region has not yet separated, but is close to breaking off, and that's a very important feature, as you'll see in some of the photos. In terms of print and image quality, tail break off and how the tail lands on the paper influences a lot of the shape of the drop, which is important for image quality. And as I mentioned before, the blowback is limited by chamber geometry. So the final graph of the firing sequence is at 24 microseconds. The drop is now left. It's shooting toward the page, and now the bubble is collapsing, and ink is refilling in through the feed. And a couple things are important about that. The actual firing frequency that you can repeat firings is determined a lot by the refill. How fast does ink get back into the chamber? And it's a design trade-off between having a wide open chamber that refills quickly and one that's too wide, causes too much blowback, and doesn't cause enough damping in the system, which I'll get to in a minute. But so there's always tuning that's going on for a specific printer to make that balance between throughput or speed and stability of the drop generator. Another important thing we'll talk more about later is the drop collapse. So it actually is like a cavitation event, essentially, where as that bubble implodes and lands on the surface of the resistor, you have it is hitting the thin film surface on the chip. And this became important as the pens started firing for longer and longer lives. It became important to engineer that surface to withstand those pressures. So I'm going to move on here to a little bit more dynamic picture of what's going on during firing. This is actually the y-axis here is drop volume or velocity can also understand is the drop volume, and versus the frequency of firing. So how fast are you repeating the cycles of the firing event? And when you're down here at low frequency, the system essentially has the time to fully equilibrate after the firing event, and the meniscus settles at the equilibrium position. If you look at the shape of the underlying curve here, what you'll notice is that this can be modeled as essentially an underdamped hydraulic system, where here you've allowed the ringing to settle out and you're back at equilibrium. There comes a point where you're firing fast enough, and this is in the kilohertz range, where the drop has not fully equilibrated, the chamber has not equilibrated after firing, and you're firing when the meniscus is below the equilibrium position, so there's less ink in the chamber, so you get a smaller drop on the page. Then as you increase the speed even more, now you're firing on what we call the bulge, where the out from the chamber, and you're getting a larger drop volume because of the enhanced volume in the chamber. Increasing the speed further, you go back through the equilibrium position, which we have a term for this called F2SS, which is frequency for the second steady state drop. So it's the point where the curve is dropping and crosses at the same equilibrium position for the low speed. As you cross through F2SS, you get to lower and lower points where you're shooting smaller and smaller droplets, to the point where down here is what we would call a multi-drop mode, where you're actually firing so fast that you get these very tiny droplets and spray, which, while it is a difficult phenomenon to control, there is one printer that is made by an unnamed competitor that actually fires in multi-drop mode and tries to control this spray, and that's a very challenging thing to do. And you do get the advantage of very small drops, which are better in terms of the graininess of the picture that you eventually get. However, the scatter of those drops is much less controlled than when you operate at the higher drop volume. So that's definitely a trade-off. Okay, so I'm going to move from the general now to more specific. The first incarnation of a drop-on-demand inkjet printer was from HP in 1984, and this is called TIJ 1.0 or Thermal Inkjet 1.0. This was the inkjet printer as well, had the same name. Some of the key features of this, one was that this was a glass substrate, and that might be pretty surprising to people now, in that silicon is overwhelmingly used as a glass substrate, or as the wafer. Technology's work is by leveraging existing equipment, existing assets, existing production lines, and at this same CP fabrication facility that was done on glass. And so because they felt like, well, gee, silicon is an awful expensive substrate, and we've got glass right here up and running, that was it did enable the technology to get started. It's, I think, a common theme you've heard from a couple people today, that if you're presenting your company with an extremely formidable investment to get into a technology, it's much more that are accepted than if you could have occasions from existing tooling investments. So some of the other things that were sort of leveraged from that was that the actual firing resistance print heads for the thermal paper that is still used somewhat in fax machines and things like that. And the principal feature that makes that a desirable film is that that binary alloy has temperature coefficient of resistance. This is really important in that during the firing pulse, that resistor heats up to something around 1,000 degrees C. And if you don't have a zero temperature coefficient of resistance, you don't get a uniform delivery of energy to the firing resistor. If the resistance is rising, as would be common with a lot of metals, it would taper off and affect the bubble nucleation and eventually the drop shape. So that couple of the other important features, the passivation layer here that you can see is made out of a composite dielectric. This is done in a plasma-enhanced CVD reactor. It's a dual layer of silicon nitride and silicon carbide. The carbide was chosen because it has extremely good wet etch resistance against virtually all wet etch chemistries. And so layers on top of it would not cause processing layer underneath of it. However, the nitride makes a better electrical insulator. And so this dual layer was chosen. And then last but not least, the orifice plate you see here is actually electroform out of nickel. And this is becoming a popular part of the toolkit at this point. But in 1984, this was really very pioneering work. I'd like to show a little bit of a close-up. This is an OCM orifice plate. You can see these are the actual ink feed holes here. And what these are in between are barriers. And they are essentially walls between adjacent chambers, hydraulic crosstalk between firing chambers. And so that's how they were kept separate in the first iteration. And that's an important thing to remember because that was changed later on. Here's just a quick photo of the business end of a TIDGE 1.0. The cellular feature there, if you look again, maybe you can see that, maybe not on your photo, but this is the area we were just looking at in high magnification. This is sort of a plenum area. This was nicknamed piano because it kind of looks like a grass end that is essentially in waiting before it comes through. The slot for this that fed ink from the main bladder of the pen was actually abrasively drilled, essentially akin to a very controlled sandblast that cut a glass wafer. Last but not least, in our business, what we really sell is print quality. And so what it all boils down to is, what does it look like on the page when you've built this pen, built it into a print engine, and then make a printer around it. In the first TIDGE 1.0, the print quality was not what you'd call spectacular by today's standards at all. The reason that was a successful product really revolved around a couple things. One, that the printer was very low cost. This was the printer was simple. And the other reason it was successful is because it was extremely quiet. The competition at this time was primarily impact dot matrix printers. It had sort of akin to those, but what it really did is enable people in an office to have a printer anywhere they wanted without having it be a massive disruption to work. And that's what got this into the business and home environments. So then in 1988, the first major evolution of TIDGE took place. This was called TIDGE 2.0. And for reasons that are now clear, they converted back to a silicon sub. And even though they did that, they still had to have a thermal barrier underneath. Can you zoom in on this portion a bit and see if I can? It's kind of a small picture, but because of the higher thermal, they were forced to put a thermal capacitor layer in between there that modulated heat flow out of the firing chamber into the wafer. Without it, it was playing just too well heat sunk to the layer underneath it. Much of the thin film structure is the same, resistor layer, same passivation. The principal things that were new were this tantalum layer on top. And tantalum is an extremely tough material in the engineering sense, and was one of the few materials they found that was able to withstand the pounding, this cavitation during bubble collapse. And so a thin layer of tantalum is on top of all the resistors. The other key feature here is they moved away from just electroformed small barriers between the parts of the chamber to a photoimageable ink barrier. And this was a pretty major breakthrough because what this allowed was much more freedom in terms of, you notice the much more complex shape of the chamber of chambers. And there is quite a bit of experimentation, both analytical, computational, and empirical experimentation to determine, what is the optimum shape to get this balance between refill speed, print quality, and the other performance features. Another thing you can still see with TIDGE 2.0 is you can see this relatively rough edge here. This is an abrasively drilled slot. It is arguable that a KOH dot batch could have been used for that. And it was investigated, but basically it was kind of a break-even proposition, and they had the abrasive drilling already up and at capacity, and so that was used again. Again, this idea of leveraging the assets that are already online. So focus a little bit on the process that makes the orifice plate now. Again, it was the top level that just makes the nozzle now. It didn't make the ink barrier, but the nozzle was still electroformed. And the way that was done is you have a piece called a mandrel, which was stainless steel. And as you're probably aware, stainless steel forms a very passivating oxide on top of it. And then the nozzle dimension was patterned in a PVC and created as a round bore with conventional photolithography. Then plating occurred only in the metal areas on the stainless steel plate. And what happens with this insulating disc, it encroaches laterally over the top of the disc. And by monitoring that lateral encroachment, we were able to control this dimension, which orifice dimension in the funnel orifice plate. Then because of the intentional pore adhesion between the electroformed layer and the stainless steel mandrel, it can be peeled off of the mandrel, and the mandrel can be reused many times before it is actually either, it gets worn out from just too many uses. A little bit of a more macro picture of the TIJ2 pen is here. You can see that what the printhead is made, it is put on a flex circuit, which allows mechanical and electrical interconnection to the printer. The pen body, the inside is filled with ink and is held with foam. If you don't have some slightly negative pressure or back pressure on the ink, it would simply drool out the front nozzles right out of the front of the pen. And so various schemes have been used. The TIJ 1.0 had an actual rubber bladder that provided some pull on the back of the ink so it did not drool out. Foam has been used, and even now there's essentially a baggy-like thing with a mechanical spring inside it, which provides, again, this back pressure to pull on the ink. This part of the factory is called intermediate and final assembly, and lines to produce this are all over the world, where the print heads are focused in a couple of fab areas that are much more confined. The TIJ 2.0 family produced substantially higher print quality. It was the first 300 DPI, and this family of pens is still producing new printers today, and it's still doing very well in the marketplace. So moving on to about 1987, 88, we can see that the next family is called TIJ 2.5S. The S is for slotted, and it retains this abrasive drilling process very much like the previous products. The principal thing that's different here is that you have underneath the TIJ process, you have an NMOS process. And this was basically required because as the number of nozzles kept rising and the amount of interconnect kept rising, it became almost impossible to have reliable interconnect to the printer. You just had too many pads that had to be planar with the printer at the same time. And so the principal feature that the FETs perform, addressing scheme. And so by turning on a pair of FETs at any given time, you enabled one nozzle to fire. And so this reduced the number of pads needed by, if you go through the math, it's 1 over the square root of n, where n is the number of pads with a direct drive scheme. So this was a breakthrough in terms of our ability to do faster and faster throughput. We can have more nozzles and not overload the printer in terms of interconnect. Here's a picture of a system we call the DBOS, drop break-off observation system. And you can see the head of the droplet, the long tail, and even a small secondary drop back here. This observation system is used extensively for characterizing what the drop shape looks like and how that tail trajectory is going to affect the image quality. Here's the
Okay, here I want to add some comment for this particular inkjet. Again, inkjet is another very important microfluid product in the world. I just give you a reference, right? Huh? Can you imagine how big this market? Huh? Globally, the market size of inkjet is 45 billion US dollar. But what's the problem? If you know how to design and fabricate this kind of inkjet, can you make money? What do you think? Huh? Do you any idea? If you learn about micro machining, and then can you really make a real product? Occupy 1% of this big market, 45 billion US dollar. Any idea about into the business of this kind of inkjet? What's problem? Any idea about this thing? I told you it's not technology. Actually, if you look at the website I just gave you through this chat room, So one of the big problem of this is not technology, it's a patent. So all the big company, they would find a patent, right? Portfolio, so that if you want to compete with HP, Epson, and many other company, it's very difficult. You understand? It's not just okay. You see, these inkjet were done by Canon, HP, and several big company. Okay, yeah. So that actually, I do have project. When I was still at UCLA, I do a project to work with Professor King and the student Professor Kevin Zheng and make this kind of the inkjet. So that let me show you. I already upload the paper on our Canva website, and then we may want to take a look about this inkjet, the work done by Professor. That time he's a peer student with Professor King. Professor King was seeing one thing. This is a high resolution of top shooting micro injectors. Okay, in terms of design, fabrication, and thing. So that again, so that of course that time Professor King worked with Professor Ho and make this kind of a product, right? So not product, it's a prototype, and then eventually I think the performance wise I think it's good, but the problem now is it's still very difficult to make a real product. Do you understand? That is the issue. So that it's not something you can really make this kind of product, right? So you have a good idea to design to make this kind of main micro machine, and then also you have a good patent portfolio, right? Otherwise, it's very difficult to make money, right? Yeah. Anyway, I just give you some additional information because I was involved in this the project on this inkjet, right, more than 20 years ago. So that I have real experience. You can look at this particular the paper for your reference. Okay. Do you have any question for this particular one? Huh? Okay, the inkjet is one of a very big market for sure. There's no doubt at all. Okay.
This is the pen that we're in. As you can see, the length of the pen, this has got nearly a half-inch swath across the page, and quite a bit larger number of nozzles than the previous generations. So if we move forward in time to the most recent developments in inkjet, there's a new family that is called TITCH 2.5E, and the E is for edge feed. The principal difference here, it uses the same drive circuitry, the same row and column addressing scheme. As far as IC fabrication and micromachining, it is very much the same. What is different is instead of an electroformed metal orifice plate, they now take the flex circuit that was there anyway and laser ablate a hole right through it. So this is done with high-powered lasers that will ablate on the order of 100 holes to 150 holes all at once through a 2 mil thick or 50 micron thick capped on circuit. And so as you can see from the picture, it still has that converging bore, which is important for drop ejection, that the drop fires straight out. And another way to get a view of this is from a technique that we've been developing, which we call micro casting. This is actually where you take the bladed flex circuit and cast epoxy over it and peel the circuit off. And what you have left is this little mesa or cone, which shows what the inside of the bore actually looked like. And this is a young technology. We're still learning a lot about this. We're learning how the various taper angles of the bore affect the drop ejection process. And this technology still has a lot of promise for us, and our newest products are being released in that right now. Just to kind of give you a little bit of an overview of the difference. So one of the driving forces for going to edge feed is saving silicon real estate. Again, as you've heard from folks earlier today, it's very important to make your chip as small as possible, keep your yield as high as possible, so that you can get the most chips out of a given wafer size. And one of the main differences is, if you see here on a slotted product, you have your nickel orifice plate on the top, the photoimageable barrier,
and either a direct drive or a TIG MOS chip underneath. And the ink slot is this abraded slot right in the center, and that the dimensional control on that is not really tight compared to normal micromachining dimensions, and there must be a lot of mechanical stability around it so that the chip doesn't crack for, again, the same stress concentration reasons. When they move to edge feed, you can see that now the chip is just one block, and so even a very high aspect ratio chip that's rather long and narrow but provides good swath height across the page and lots of nozzles can be rather narrow and still be very mechanically easy to handle and not fragile. And the reason is you actually feed the ink up over the side and then shoot it through the ablated bores in the flex circuit. So that brings us pretty much up to date on the products that have been released to date. There's obviously a lot of research at HP and other companies in these areas. And I wanted to spend a little time as we close up on and talk a little bit about where they're going. A couple of the main parameters that we use to monitor our business are drop weight, essentially how big is this? There's a lot of interaction with the media and so forth, but that's our gauge of spot size. And nozzle count in the other measure of how fast is a printer. People want faster and faster. We have this problem of constantly being compared to our sibling division in Boise that makes laser jets, and they want to know why we can't do 15 pages a minute with this technology and come to expect it. So we're working very hard to deliver higher and higher levels of throughput. And finally, just to look at where the market is going. So in terms of drop weight, this curve is pretty telling in terms of where we're going. The first inkjet printer, by the way, for obvious reasons, every time you fire one of these things, it's more or less like a small volcano. And so they tend to get names that are representative of that. The first St. Helens pen in 1984 had about 180 nanogram or picoliter, if you're talking about water, drop weight, and that's been steadily falling. And the interesting thing to note there is that we're now down in the 30 picoliter range, and down into the 10 picoliter range, the dot no longer becomes discernible as a separate entity to the human eye, and we go from being able to do just text and graphics to actual rendering of photographic images. As the drop volume decreases, though, if you didn't compensate somehow, the printer would actually get slower because you have to put down more dots. And so one of the other driving forces in them is always more and more nozzles per pen. That's kept pace with the falling drop volume. We've got up to 300 nozzles per pen at this point, and actually, as there are more than one pen per printer now, this curve is accentuated even farther. Last but not least, just a look at kind of the most recent data I have and an extrapolation of where it's going in 97 and beyond. This is kind of a view of how the inkjet printer market is with HP and other folks, and it's still in a very explosive stage. There's more and more technologies being brought to bear on this problem, and as the amount of computers and so forth keeps rising, very bright for bringing this technology to more and more people. And then last but not least, I'd like to just acknowledge all the other folks at HP. I'm very much a lot of people that have done the work there, and just want to say thank you to all of them. CJ?
We will have a couple of questions. We have okay, doesn't look like we have incoming phone call. I think we'll just, no calls, okay. I think we'll just go ahead and start our 30-minute recap. So far, you have heard And these by no means complete the exhaustive list of MEMS product. Rather, products have been by us to represent different technologies, surface micromachining and bulk micromachining, and different markets, automotive, biomedical, and consumer products, and softwares. And they function from very electronically to purely mechanically. And you've also seen that they can be built in-house with a dedicated fab line, or a small lab, or even with no facility, depending on. I hope you all gain valuable knowledge today relevant to your own unique situation. Now, during this last half hour, we begin by bringing back all our presenters for our question and answers, create, and recap. Dr. Rich Payne from Analog Devices, Dr. James Jaron-Monte, SSI Technologies, Mr. Hugh Miller for the microelectronics, EG&G IC sensors, Mr. Chris Beatty, HP. For callers, please address your questions of the panel if it is based on their presentation, unless your question is a general one. Now, while we receive the phone calls, we have quite a few questions received throughout the day through fax. So I will start with some fax questions. Let me see. I have a couple of questions for Dr. Richard Payne. This question is from JPL. Deborah, I have a hard time to see the last name, so I'll just call Deborah. The question goes, do you have any kind of backup or safety associated with your analog sensor? For instance, if the automobile is in an accident, which does not trigger the sensor, but damages the heads, there is going to be a controller.
Okay, I guess the really, answering that question, in the first place, the sensor has within it a self-test safely in passing, but every time the car is started, and in some systems, some on a more continuous basis, electrostatic voltages are imposed across the sensor, and it's motion observed to make sure that the sensor is active and working properly. So that the way that the sensor itself is assured. Now in the system, almost all of the systems for airbag deployment have what's called the safing sensor. These aren't things that we do, but they're things that our customers do in building the complete system. The safing sensor is a mechanical switch that operates at a low G range. So a bump in the road might set it off, but it's a switch which must be enabled at the same time as the airbag algorithm, and a fire control signal is issued. So there's a backup sensor within the system. And some of the future systems, there's both vector resolution, but also backup for the sensor. But finally, the sensor itself operates over only one part within a factor of 10 to the fourth or 10 to the fifth away from any limit. In other words, it would take thousands and thousands of Gs to move the sensor to the stops. Sorry about that. So that can't really experience thousands of Gs once it's inside a box inside a car. Otherwise, the car would be totally destroyed. So it's very safe in the environment, reach the braking strength.
Okay, we have one question incoming call. Bill, are we ready? Go ahead.
Hi, my name is Anand Govind, working in the CAL's Electronic Packaging Research Center at the University of Maryland. I guess my question is for Richard Payne. He was talking about their move from the hermetically sealed packages to the dips and the surface mount packages. and I was wondering whether they actually moved towards plastic encapsulated microcircuits and what specific advantages they had in that move, and also the kind of challenges they faced in making that move.
Okay. Well, the dip in the dip packages and actually surface mount package that I showed were a SUR-dip construction or a SUR-pack construction in the case of the surface mount package. Any sensor that has to have a moving part has to have a cavity, and the long-term approach is to put that cavity on the wafer, but the shorter term and what we've done so far is to use the package cavity. So those also are hermetic packages. The issues associated with plastic packaging revolve around stress. There are thousands of psi in the molding process, and the sensors are indeed displacement sensors that measure hundreds of angstroms, so that it is indeed an interesting challenge to do a plastic package, although we certainly are working on that and have done some.
Well, I want to make a comment for this particular reply. Again, this video was in 1996, so that now, after almost 20 years, now all the MEMS surrounded in smartphone, right? Motion sensor, they use plastic packaging because local and cheaper, right? And your MEMS sensor in smartphone is much smaller, so that the stress problem is much less. So that you can say 20 years ago when they make the product for the MEMS surround for airbag and car, that time the sensor is still very big, right? So that they use metal, right, for best packaging. Okay, so that's still different.
He was talking about extended 3-year periods of testing for before a product comes onto the market, and I was wondering if they really do accelerated test, and if they do accelerated testing, what kind of testing did they use for their product?
They do both accelerated testing and field testing. Accelerated testing is quickly acquire some data to evaluate the durability and feasibility of a product, but there's kind of no substitution for field testing as well. Some of the durability testing they may do are temp cycling, abrasive flow testing, testing at high temperatures, testing at low temperatures. There's a number of accelerated testing that you can do, but to do in general is also to have field tested units that have been out in the field. As soon as they've passed a point of feasibility, they're put on fully durable and how long lasting these products are going to be out in the market. This is a very important part of the testing. But Ford is very careful about trying to make any sorts of last minute changes. Even though they're mixing they could do, they prefer to have some field type testing as well.
Thank you for the question and answer.
Well, I also want to make additional comment for this MEMS accelerometer, right? Now, people also try to make the MEMS sensor with machine learning, the AI, so that this become the one of the important trend now, right? So that I would say in the near future, I say more and more MEMS sensor will install this kind of AI, right? So that's MEMS motion sensor, right? With machine learning, with AI. So that's the new trend, right? So that I just give you additional new product made by ST Microelectronics. They really try to integrate with MEMS accelerometer and the machine learning. Okay.
While we wait more phone calls, I will again go with some questions we had earlier. This question is to Dr. Hal German. One of the questions is, why do you use silicon for fluidic devices compared to traditional materials, for example, stainless steel?
Stainless steel is a very fine material for doing a wide variety of parts. However, it's relatively difficult to make the kinds of structures that we would like to make in stainless steel. the kinds of etching and the kinds of depositions of other materials on the stainless steel are relatively difficult, and the technology doesn't exist in many cases to do the kinds of things that we would like to do. Silicon is a reasonably inert material in many respects, and it can be coated with the variety of materials, particularly nitrides and the like, as has been described in some cases earlier today, to make it more resistant to a lot of the materials that one would like to have it resistant to. This problem is much more severe in devices than perhaps some accelerometers in particular, which can be, as Richie mentioned, hermetically packaged in some relatively robust ceramic packages. Essentially, by definition, any fluidic device has to be exposed to some fluid, and therefore has to be able to be resistant to corrosion or other problems associated with that fluid. Unfortunately, this generally means that this problem has to be addressed on a case-by-case basis, and that may mean that a particular part may only be applicable to a certain range of fluids or temperatures or conditions, rather than perhaps a wider range of conditions that it might be resistant to if it was made from a stainless steel or a more corrosion-resistant material.
Okay, we now have one phone call. Okay, Bill, are we ready? Phone question? Okay, we are ready. Go ahead.
Hello. Hi, my name is Vinod Jain. I'm a consultant at Booz Allen and Hamilton Inc. I'm calling you from University of Maryland, and we do methodologies for our clients. And I wanted to ask a general question. Can you identify some generic barriers and incentives in commercialization of these MEMS products? Essentially, what are the lessons learned?
What are the lessons learned? I think Chris would like to answer one question first.
So I think one of the things you saw today was that one of the barriers is just, as always, in any new business, is going to be capital. And so IC fab and micromachining are very capital-intense processes. And so where it is available, leveraging either old assets or existing assets that are online within your company or in a partner.
You may have something to say about, from the viewpoint of automobile industry.
I don't know about the automobile industry in general, but from the creation of MEMS devices to the packaging of MEMS devices, it's an interesting lesson. The thing about that, in the MEMS world, where it's always constantly talking about microns, and we may be assembling something or creating something in a very clean Class 10 type of environment, while this device way in an entirely different environment, clean by their particular standards, but not clean by clean room standards. And they have totally different levels of awareness. What we take for granted in our awareness, that we don't even think of lessons learned in there, deals with technology transferring and really being able to communicate between, say, the micro environment versus the macro environment.
Thank you. This is a very important question, I believe. So, and also we have a little more time than we originally planned for this recap session. So I will, I think everybody has something to say about this question. Rich showed that he's interested to answer some.
Yes, I think there's an important lesson certainly that I learned that I never would have quite believed before this experience was people to accept sort of new technology solutions, despite order of magnitude improvement in size, despite an order of magnitude improvement in cost. There were still a lot of people that sort of were afraid of something that sort of hadn't been done before. Maybe it's a lesson learned for startups, and I had the good medium-sized company that had a lot of revenue from it. It's a slow process, a market that just isn't existing, a market in which you don't just replace an existing solution into a socket where you have to do something slightly differently.
Okay, we have a phone call waiting, but I will make the rest of two members to answer to this question. So,
yeah, I guess the point I was going to make is that I think we underestimate either the development cost or the time to market for some of these. This is particularly true if a number of different companies need to be involved, which is often the case. Often the MEMS device is an enabling device for some larger system, so that first the idea has to be developed and some engineering studies done. Then the MEMS devices typically have to be made. They have to be supplied usually to an end user, which then has a job of developing a system and getting a system that's manufacturable out there. Usually that customer is not willing to spend much money doing parallel development of a system without the silicon part actually existing. It's difficult to convince people that either something can be done or to guarantee the performance of a particular part going in. So that means that they're two separate development efforts, and that they go to market with something from the initial concept. I think you've seen for the people who have put up timelines is often on the order of 10 years.
We have two phone calls waiting with Jim for this session.
Well, I think that my colleague has done a very good job covering the areas of the business issues, the education issue, and also the personal attitudes some people have for new technology. What I would like to add is that the lesson we've learned is that packaging MEMS devices is by no means a known science, that each individual application sometimes requires its own individual package, especially when it comes to MEMS devices that have to interact with their environment and can't be isolated from the environment, as is the case with the accelerometer that can be encapsulated and kept away from what's around it. In other devices that are either fluidic or our case pressure sensor, we have to come in contact with that environment, and we have to not only interact with it, but be protected against it. So it's kind of, you want both sides of the pie. Excuse me.
Okay, well, thank you very much for all these excellent answers. These are typical questions we hear in MEMS area from people new. As we covered, what do your company has? What kind of asset do you have? What kind of technical capability you have? And also, many times we hear about the psychology, totally new technology. And take one question from our incoming phone call. Are we ready with one question?
Hello?
Hello, can you speak up a little bit?
Okay.
Yes, can you?
Hello?
Very good. Yes.
Yeah, this is Dr. Kanglik from Rajasthan Institute of Technology. I have a question for Dr. Beatty. The question, hello?
Yes, go ahead.
Yeah, and lasers and high voltage discharges were being considered. What are the MEMS issues? Whether such things are possible to be integrated in thousands and thousands of units, and whether the technology is ready to head in that direction, or what are the roadblocks? I have to hang up and go to your answer. Is the question clear?
Let me rephrase. You're asking what are the integration roadblocks to large numbers of firing resistors? Is that the question?
High voltage discharge type of heating methods to generate homogeneous nucleation on the heater surface, so that the speed can be increased quite a bit.
Okay.
Okay, can I hang up?
Yes. So I guess I'll give him a minute to jog back to wherever he has to go. So I guess the first and most important thing I can think of that is a real impediment with homogeneous boiling is cleanliness. If you have a surface that is either chemically or even mechanically not clean, not smooth, run into problems where you'll get heterogeneous sites that will nucleate a bubble prematurely. And I think regardless of the firing mechanism, laser driven or other, those sorts of irregularities in the surface are going to cause misfiring of some form or another. They take a lot of different shapes. The biggest to me, other things that might be a problem for a homogeneous surface, if you're going to use a laser driver or high voltage, it's uniformity of energy delivery. Same problem if you have in reverse. If you deliver, even if it's a smooth surface, and you deliver the energy non-uniformly, you won't get nucleate in one corner, one spot. And again, if it's thermal, that boils down to variations in sheet resistance of films and things like that. Making sure that you deliver the energy uniformly, and then that the surface is able to accept it and create the plate-like boiling to get a consistent dry bubble.
Great. Thank you, Chris.
Okay, I think we almost run out of time. So I also add additional comment about this additional the main sensor, right? So that the main motion sensor now will become, I think, one of a very important area is for Industrial 4.0. Especially, they are very useful for predictive maintenance, right? So that how can we install a large number of IoT main sensor, right, for large machine, for this kind of monitoring about the health condition of machine, for industrial control, right, in that 4.0. I think this is one of a new trend now for this IoT, right? IoT is, I think people say is one of important big business potential for this main sensor, right? But IoT sensor have the what? Low power and also the reliable, right? And then connect to internet, right? With collection of large number of data from main sensor, and then how use AI. So try to look at this kind of predictive maintenance and then even control about all the machine, right? For Industrial 4.0, I would say this is one of a new trend. Now people really want to work on this area. Okay, so that I don't know. Do you have any question for today's lectures? Any question for today's lectures? If one and then you ask a question, of course. Okay, I understand. So that we do have some issue for this kind of term project. Some of the students try to reply that you probably have a difficulty to compare with your team member for the project. Again, I recommend you try to have some this kind of video conference through the Zoom or some other social media. Make sure still have some reasonable good progress for your project. Do you understand? The second thing is our department asked me to announce that actually for this particular course, again, we have no final exams, but we have term project, presentation report, and then we allow you to have this kind of change the grading from the normal or grading policy to pass or fail, so that if think you have a problem and because this kind of destruction of the original lecture, so that you can request to change this kind of grading policy. Okay, so that is something I think very important for all of you, right? So that of course I will also make announcement on our campus website, so that you have option, right? If you think there's no problem, no, you can do a good job for the project, no problem. If you think there's some problem because this kind of disruption of a normal lectures and things, so that you can request to change to the pass or fail or grade. Okay. I see. Do you have any question about the project? Any question? If a question is, you cannot try to ask me individually or try to post a question on the campus website. I think we almost run the end of today's lectures again, so that so I will try to put this record video on our campus website. Okay. Again, to do any question for today's lectures? Huh? No? If no, then probably I think that's it for today's lecture. So that again, we can keep in touch. And then again, you have some problem about your project, please let me know so that I give you additional information. Okay. Okay, that's it for today's lectures. Okay.